The reinforcement learning techniques that are used nowadays are very quick and give immediate results for less complex environments using the gradient-based policy optimizations. The gradient-based policies are competitive and not collaborative. So what if we need long-lasting results for more complex environments, having agents with complex tasks to perform? There are many world environments where we do not have the ability to modify the environments, and performing reinforcement learning on the real-world tasks are really time-consuming. So to overcome that problem, this paper tries to solve that issue with the help for curriculum learning and population-based training. To design a sequence of tasks using transfer learning for an agent to train on, such that final performance or learning speed is improved. PBT has the ability to modify the hyperparameters of the network while training. The main idea behind the mix. Multiple agents that are arranged in learning complexity, shown above, are treated as one mix. Distillation is done in such a way that the complex agents are matched with the simpler ones early on. Mixing coefficient is controlled such that ultimately complex target agent is used to generate experience. Let's assume we are given a sequence of trainable agents 1, with corresponding policies pi1, pi_k, each parametrized with some theta I theta which can share some parameters. The aim is to train pi_k, while all remaining agents are there to induce faster, easier learning. Let's introduce categorical random variable c, cat1, k, alpha, probability mass function p, c equals I equals alpha I, which will be used to select a policy at a given time. The point of mix. Initially the PMF should have alpha 1 equals 1, and near the end of training alpha k equals 1, thus allowing the curriculum of policies from simple pi1 to the target 1 pi k. Now, it should be trained in such a way which maximizes long-lasting increase of performance and share knowledge together, unlike those gradients. To address this issue, we will be using a distillation like cost D, which will align the policies together. The final optimization problem we consider is just a weighted sum of the original L_RL loss below, applied to the control policy pi_m and the knowledge transfer loss. Now, let's understand the mix. For simplicity, we consider the case of k equals 2. Consider the problem of ensuring that final policy, pi2, matches the simpler policy, pi1, while having access to samples from the control policy, pi_m, same as previous zone. For simplicity, we define Rm. The 1 minus alpha term is introduced so that the distillation cost disappears when we switch to pi2. Alpha is the variable used in the population mass function equation. First equation. This is the first equation. An important component of the proposed method is how to set values of alpha through time. For simplicity, let us again consider the case of k equals 2, where 1 needs just a single alpha, as c now comes from Bernoulli distribution, which we treat as a function of time t. Online hyperparameter tuning. Since alpha changes through time, one cannot use typical hyperparameter tuning techniques, as the space of possible values is exponential in number of time steps. Alpha equals alpha 1, alpha t, element of 4 takas minus 1, where 4k denotes ak. Dimensional simplex. To solve this issue, we use population-based training, PBT. Population-based training, PBT, keeps a population of agents trained in parallel, in order to optimize hyperparameters through time while training, and periodically query each other to check how well they are doing relative to others. Badly performing agents copy the weights, neural network parameters, of stronger agents and perform local modifications of their hyperparameters. This ability of PBT to modify hyperparameters throughout a single training run makes it possible to discover powerful adaptive strategies, e.g. auto-tuned learning rate annealing schedules. This way, poorly performing agents are used to explore the hyperparameter space. So, we need to define two functions, eval, which measures how strong a current agent is, explore, which defines how to instigate the hyperparameters. Now, we should use one of the two schemes mentioned below, depending on the characteristics of the problem we are interested in. If models is having performance improvement by switching from simple to the more complex model, Thena, provide eval with performance, i.e. reward over k episodes, of the mixed policy. B, for an explore function for alpha we randomly add or subtract a fixed value, truncating between 0 and 1. Thus, once there is a significant benefit of switching to more complex 1, PBT will do it automatically. Point 2. When we want to switch from an unconstrained architecture to some specific, heavily constrained one, where there may not be an obvious benefit in performance from switching, when training a multitask policy from constituent single-task policies, we can make eval an independent evaluation job which only looks at performance of an agent with alpha k equals 1. This way we directly optimize for the final performance of the model of interest, but at the cost of additional evaluations needed for PBT. Let's test and analyze whether our new M. We will now consider 3 sets of reinforcement learning experiments which can be scaled to large and complex action spaces, complexities of agents architecture and learning multitask policy. In all the process, we initialize alpha at around 0 and analyze its adaptation through time. Note that even though in the experimental sections we use k equals 2, the actual curriculum goes through potentially infinitely many agents being a result of mixing between pi1 and pi2, unless otherwise stated. The eval function returns average rewards from last 30 episodes of the control policy. The Environment Suite of DeepMind Lab offers a range of challenging 3D, first-person view-based tasks, see Appendix, for RL agents. Agents perceive 96 × 72 pixel-based RGB observations, at 60 FPS and can move, rotate, jump and tag built-in bots. The action space is complex, represented in 6-dimensional vector where 2 action group are very high resolution, rotation and looking up, down actions, and remaining 4 are low resolution actions, moving forward, backward or not moving at all, shooting or not shooting, etc. Here, we use 9 actions to construct pi1, the simple policy, small action space. Similarly to the research in continuous control using diagonal Gaussian distributions, we use a factorized policy, pi2, a 1, a 2, a 6, s equals j equals 1 pi j, aj, s, which we refer to as big action space. In order to be able to mix these two policies, we map pi1 actions onto the corresponding ones in the action space of pi2, the mixing of values between networks of agents shown in the figure below. The paper also discussed shared head and masked KL techniques, but both are more than M. Mix. Fig. Training in action spaces experiments. When plotting alpha through time, Fig. 5 left, we see that the agent switches fully to the big action space early on, thus showing that small action space was useful only for initial phase of learning. This is further confirmed by looking at how varied the actions taken by the agent are through training. Fig. 5 right shows how the marginal distribution over actions evolves through time. We see that new actions are unlocked through training, and further that the final distribution is more entropic than the initial one, which means that more entropy leads to more stability. We substitute the LSTM with a linear projection from the processed convolutional signal. We share both the convolutional modules as well as the policy, value function projections. The experiments are focused on various navigation tasks. On one hand, reactive policies, which can be represented solely by a feed-forward policy, should learn reasonably quickly to move around and explore, while on the other hand, recurrent networks, which have memory, are needed to maximize the final performance, by either learning to navigate new maze layouts, explore object location small, or avoiding, seeking, explored unsuccessful, successful paths through the maze. Fig 6M. Fig 7 Fig8 leads to 2 observations. The green curve switches late to LSTM due to complexity in the level of game. The model, blue curve, has the ability to switch back to the mixture policy if needed. As a final proof of concept, we consider the task of learning a single policy capable of solving multiple RL problems at the same time. The basic approach for this sort of task is to train a model in a mixture of environments or equivalently to train a shared model in multiple environments in parallel. This type of training can suffer from two drawbacks. It is heavily reward-scale dependent, and will be biased toward high reward environments. Environments that are easy to train provide a lot of updates for the model and consequently can also bias the solution towards themselves. Let's take a look at the results. Fig 9.1 is explore object location small, which has high rewards and a steep initial learning curve. Lots of reward signal coming from gathering apples. In remaining two problems, training is hard. The agent is interacting with other bots as well as complex mechanics, pickup bonuses, tagging floors, etc. The multitask solution focuses on solving the navigation task, while performing comparatively poorly on the more challenging problems. To apply M. Crucially, agents share convolutional layers but have independent LSTMs. Training is done in a multitask way, but the control policy in each environment is again a mixture between the task-specific PI, the specialist, and PyMT, centralized agent. Since it is no longer beneficial to switch to the centralized policy, we use the performance of PyMT, i.e. the central policy, as the optimization criterion, eval, for PBT, instead of the control policy. We evaluate both the performance of the mixture and the centralized agent independently. Fig. 9 shows per task performance of the proposed method. One can notice much more uniform performance, M. One of the reasons of this success is the fact that knowledge transfer is done in policy space, which is invariant to reward scaling. While the agent can still focus purely on high-reward environments once it has switched to using only the central policy, this inductive bias in training with M. Over time, the component weightings of this mixture are adapted such that at the end of training we are left with a single active component consisting of the most complex agent. Also, improved and accelerated performance in complex environment. Collection of agents is bound together as a single composite whole using a mixture policy. Information can be shared between the components via shared experience or shared architectural elements, and also through a distillation like KL matching loss.